Welcome, ladies and gentlemen, to the Wednesday afternoon session. We have two speakers, as usual. There probably are smaller statisticians in the world, but I don't know them, and I'm sure if they exist, none of them have a bigger stature than our speaker this afternoon, our first speaker, Professor Bimal K. Sinha from the University in Maryland, Baltimore County. He is a native and a graduate from the University of Calcutta. He taught for a short period at the Calcutta branch of the Indian Statistical Institute and also for a short period in Pittsburgh in the university there, University of Pittsburgh. And now he has his present job as professor and head of the statistics section at the university I mentioned. His talk this afternoon is Robust Optimum Invariant Tests for Variance Components. And it's a great pleasure to welcome him. I know him from time in Calcutta, and you'll find him a most stimulating speaker.
Well, I wish to thank the organizers of the conference for kindly inviting me. I was invited in the first International Tampere conference in 1983, and I find that this time it is much bigger and, of course, better. This is a joint work with my student Rita, who moved to the University of Toronto. There are two parts in the talk. In the first part, I look at invariant models. So let us look at the general mixed model involving the fixed effects beta and the random components epsilon 1, epsilon k, and the last part is epsilon 0. And this could be, for example, the random treatment effects or the random block effects or the random interaction, and epsilon 0 here stands for the random error component. And the usual assumption about the random effects in this mixed model is that the components epsilon i's, they are independently normal with mean 0, and they are all uncorrelated with common variance sigma I squares, and of course it's different for I equal to 1 to k and I equal to 0, so that we have the model y is normal with x beta as the mean, and the covariance matrix of y is summation sigma I square, zi prime, and the zi's and x, these are the known design matrices, and beta is the fixed vector of regression coefficients, and the sigma 0 squares are the unknown variance components. I put zi prime equal to vi so that I can write the model in this form: y is normal with x beta and summation sigma I square vi. The parameter space here is the last component sigma 0 square corresponds to the error variance, which is strictly positive, and the other components of variance sigma I squares, they are non-negative, and typically the last matrix here B0 is the identity I. And the problem is I want to test if one of the components of variance is 0, alternative it's strictly positive, for some I greater than 0. Now it is possible that we might be interested in testing simultaneously several components of variance equal to 0. But let me look at the first, or just one component only. What happens if the epsilons are fixed effects? In that case, the model will be, if I regard all the epsilons up to k as fixed, then we have essentially a fixed effects model. All these are fixed effects, and only the last component, which is the random error component, that's the random part, measurement error. And in that case, if I want to test that the ith vector of fixed effects epsilon I is 0, alternative it is different from 0, for some I, then the well-known result is the following, that the ANOVA F test is optimum. Optimum in the sense of, if the dimension of this is 1, essentially it's one element, then it is UMPU, and more generally, if the dimension is more than 1, it is uniformly most powerful invariant in general. And the proof is given in Lehman 1959, the classical book on testing of hypothesis under normal theory. On the other hand, the proof appears in Carrier 1981 and also in Carrier and Sinha 1985. If we replace the assumption of normality by more general distributions of the last component epsilon 0, namely, it could be either spherically symmetric or left orthogonally invariant distributions. I should also mention that there is a paper, very interesting paper by Seifert in 1979, which discusses the properties of the F test under a general balanced mixed model. And the problem is to test for fixed effects, like here. We are assuming that these are fixed. All right, but of course, my problem is what happens if the epsilons are random, so that we have a mixed effects model, and this is the setup, and the question is, how do we test the null hypothesis that the ith variance component sigma I square is 0, alternative that is positive. It is surprising to note that a lot of work has been done on the dual problem of estimation of the variance components. And an excellent reference is the book by Dr. Clefe and Professor Rao, entitled Estimation of Variance Components and Its Applications. On the other hand, for testing problem, although quite a lot of work has been done, but not a great deal of attention has been paid on the optimality of tests. So I'll summarize briefly what is the literature on tests of variance components. If you look at any standard textbook like the book by Searle or the recent book by Steve Arnold, you'll find that when it comes to tests on variance components, what is recommended mostly is the ANOVA-based F tests for both balanced and unbalanced models. So what you do, you look at the ANOVA table, you have the different sources of variation, the different sums of squares, then you compute the MS, the mean squares, but this time under the assumption that you have a mixed effects model, not a fixed effects model. So you can compute the MS, and then you can look at the appropriate ratios, and you can compute the F tests. And for most of these problems, the F test will provide exact similar tests. And for unbalanced models, it was first done by Wald in the 40s, and then of course we have a series of papers here. And Professor Khoury, who is one of the participants, has also done quite a good amount of work on providing exact similar tests for balanced and unbalanced models. But the question I raise is, what are the optimum properties of these tests? Or is it possible to derive an optimum test for these problems? And by optimality here, I mean exact non-asymptotic for fixed sample size, whether there is an optimum test. Okay, the first result here is the following. For balanced models, as you can expect, the F tests are uniformly most powerful, invariant, unbiased. And that if the dimension is, that's true if k is more than 1. K is the number of variance components other than the last component, sigma 0 square. So you have sigma 1, sigma 2, sigma k. So if that k is more than 1, the test will be uniformly most powerful, invariant, unbiased. On the other hand, for k equal to 1, the test will be uniformly most powerful, invariant. And you might recall a very old paper by Harbeck in 1959 Annals, where he attempted to prove it, but it's not quite clear whether he got the result or not. So this result, I looked at different textbooks, and it's not given anywhere. So it looks like it's a new result. And another feature of the result here is we don't have to assume, as is well known by now, you don't have to assume normality of the error components. We can do away with normality. So what I assume that the joint distribution of y has min x beta and dispersion matrix summation sigma square vi. So instead of assuming that phi is exponential, which will give you the normal distribution of y, you can assume any arbitrary structure like this, or phi is very arbitrary, except that it satisfies the integrability condition. So under this setup, we can, and if we assume that the design is balanced, then we get the optimality of the ANOVA F-test, which is nice in a way because we have been using F-test for a long time, so it's satisfying to know that the F-test enjoys the optimality property. And the proof here uses Weismann's representation theorem. And I should also mention that Seifert in 1979, under this setup, assuming of course normality, he proved that the ANOVA F-tests are also UMPI U. So what we did here, instead of for the fixed effects, we proved it for the random variance components model. Now, let's see what happens in the unbalanced situation. So the second result is the following. It turns out that for unbalanced models, the optimality of the ANOVA F-test is no longer valid. So what I have demonstrated here, what happens in the simplest unbalanced situation, namely one-way unbalanced model. So we have the replications Ni corresponding to the ith treatment. So you have the usual model mu plus tau I plus epsilon ij, and we assume that these are the tau i's, they are all uncorrelated with min 0 and variance sigma square tau, and the random error component, it has variance sigma square. And what I do, I write all the, you put all the yij's, stack them up, and denote this by a vector y. And to get a canonical representation, let's denote by capital D the block diagonal matrix d1, d2, dk, or di is orthogonal ni by ni, with the first row given by ni to the power minus f, and they are all the same. Then from y, you define z, which is d times y, and assume that the distribution of z is given by this. If I assume phi to be exponential, then z is of course normal, and you can recognize this form. This is the within sum of squares SSW yij minus ya bar square, and zi1s are the square root of ni y bar I dot, and this is the form you have, or the joint distribution of the zi's. Now here phi is arbitrary and more general than normal. In the balanced case, when all the ni's are equal, you can see that the whole thing, we can simplify it further, and you get the between sum of squares and the within sum of squares, and of course the grand mean y bar as the sufficient statistics for three parameters mu, delta, and sigma square. By delta I denote the ratio sigma tau square by sigma square. So you have three sufficient statistics for three parameters, and one can show that the joint distribution is complete, and one can, that's what happens in the balanced case. In the unbalanced case, however, you can see from here that since all the ni's are unequal, you have the sufficient statistics more than three, like this sum of squares and each zi1, that remains there. So you have a whole bunch of sufficient statistics for the three parameters. And of course now it is the incomplete situation. So in the unbalanced case you have incomplete sufficient statistics. So even if I assume that, and as a matter of fact, even if I assume that phi is normal, it doesn't help. You still have too many sufficient statistics for the three parameters. So the incompleteness is still there, even with the assumption of normality. And the problem is, how do I test that delta is 0, alternative delta is positive, because delta is the ratio of the components of variances. Okay, it turns out that here there is no UMPI test, unlike in the balanced situation. However, it is not difficult to derive a locally best invariant test, and the group is the usual translation and scale change. And since I have not assumed that phi is exponential, in other words, the distribution of z is normal, we cannot use the standard normal theory or the exponential model, but we can use the representation theorem due to Weismann. So what we do, we choose as a left invariant measure on the group G this dA dC over c square, and then there's some little bit of calculations, but immediately you can compute the ratio of the distribution of the maximal invariant, what non-null to null. So that ratio, this is the general form, and in this particular problem, if I compute it, then it turns out to be this form. So the ratio depends only on the maximal invariant parameter delta, and it's given by this. I didn't write QZ delta, it's quite long, and Z0 is evaluated at delta is equal to 0. But what happens in the balanced case, the same thing, except that the NIs are all equal, and we find that our delta is strictly increasing in the usual F test or the F statistic, the between sum of squares over the within sum of squares. And that gives us the UMPI property of the F test. In the unbalanced case, however, R delta is not monotone enough. As a matter of fact, there is no test statistic in which R delta is monotone. So what we can do, we can expand R delta locally when R delta is equal to 0, and this is the expansion we get. And the last term here is small o delta uniformly in all z. And that's very important if you want to derive the LBI test. So it's important that the last term remains small o delta uniformly in z, and this is the expansion we get for some psi z. And that implies that the test based on psi z is locally best invariant. And in particular, if I replace z by y, if I express everything in terms of y, that is the test I get. And it's kind of surprising that it's not the usual F test. The usual F test will have Ni in the numerator. If I had Ni, then of course it's the between sum of squares over between plus within. That gives the F test. But here you don't have Ni, the Ni square. So this is not the F test. I can mention that Sporsmol in 1967, he also did similar calculations, and he showed that the F test is asymptotically best invariant for large delta. But here we are concerned with the local alternative delta near 0. That gives the in the case of, that was for one-way unbalanced. In the case of multi-way unbalanced models, the open problems are the following. First thing is derivation of optimum invariant tests for fixed effects and also for variance components in the case of unbalanced models. And this is currently under investigation. What we expect to get better similar tests than F tests for both the problems. And another thing we should investigate, the sample size consistency and the parameter consistency of these LBI tests. Hopefully, as far as the sample size consistency is concerned, I don't see any problem, but hopefully parameter consistency will go through in this particular problem. Because essentially, after data reduction through invariance, you have one parameter problem. So hopefully, parameter consistency will go through. All right, in the second part of the talk, I have the multivariate balanced model. So yesterday we listened to Professor Perlman. So the same setup I have here, the MANOVA model in canonical form. The first, these are all matrices, y1, y2, y3, and the mean matrix is m1, m2, and this is 0, and this is the random error component E, and we assume that E is normal I cross canonical product sigma, and sigma is positive definite unknown. And in this problem, in this setup, we test whether m1 is 0 against m1 is non-zero. This is the MANOVA problem, and there are many tests based on the roots of this matrix. For example, we have the maximum root test, then the trace test, and the lolly-hoteling test, like that. This is the fixed effect MANOVA model. I'll consider the mixed MANOVA model, assuming that M1 here is random. So the mixed MANOVA model can be thought of in this form. M2 is still fixed, the second component here is still fixed, but M1 is random. And I assume that M1 is normal with mean 0 and variance covariance matrix given by sigma 1 square. So it's a scalar multiple of the error term, I cross sigma multiplied by sigma 1 square. So that gives y1 in this form, y2 and y3. And the problem is to test whether small sigma 1 square is 0, alternative sigma 1 square positive. So this can be thought of as the mixed MANOVA model. And I looked at the literature. The first time it was treated by Roy and Ganadeshekhan in 1959 annals. They looked at this problem. Of course, they took N2 to be 0, which means they didn't have Y2. They had only Y1 and Y3. And they proposed the maximum root test for this problem. And the question is whether the maximum root test is any optimum, it has any optimum property. If not, what should be an optimum test for this problem? Again, I assume that N2 is greater than or equal to 0, so that Y2 can be there, so that we have a genuine mixed MANOVA model. And one can write down the joint distribution of Y1, Y2, Y3. I did that, except that in this joint distribution, if you assume normality, then you have the exponential term. Instead of the exponential term, I have an arbitrary q here. All right? So I don't have to assume that the joint distribution is normal. An arbitrary q will do, satisfying some conditions here. Okay. And the result is the following. Again, for testing sigma 1 square 0, there is a certain group here which keeps the problem invariant. And so one can look at the maximal invariant, and one can use Weismann's representation theorem. So if I do that, then the result is the following. Put eta equal to sigma 1 square over 1 plus sigma 1 square. Then the ratio, it can be computed directly, the ratio of the distribution of the non-null distribution of T, which is a maximal invariant over the null, is directly of this form. Or small r is n1 plus n3 by 2. So if I have dimension equal to 1, or the first matrix y1, if it is of order 1 by p, if n1 is 1, so the minimum of p and n1 is 1, then one can show that the ratio is strictly increasing in the trace criterion. So that shows that there is a UMPI test for this problem based on the trace. On the other hand, if p is greater than 1 and n1 is greater than 1, then there is no UMPI test, but one can expand it, and it turns out that there is an LBI test, again based on the statistic U, which is the trace of this. Eta is sigma 1 square over 1 plus sigma 1 square. Right. So the test based on U is LBI. In both the cases, we see that the trace test is better than the maximum root test. All right. Now, as a matter of in this problem and also in the previous problem, whenever you compute the ratio, it turns out to be independent of Q, so which means we have the robust optimality of the trace test. And the question, in light of Professor Perlman's talk yesterday, whether the trace test, it has the sample size consistency property and or the parameter consistency property under the random. This will be purely random if we assume that N2 is 0, as Roy and Ganadeshekhan did, and it will be a mixed MANOVA model if I assume that N2 is positive. So whether under this setup the trace test has these properties. And my guess is probably yes, because this is not the same as the fixed effects MANOVA model. So probably we'll have the probability.